Great. Thank you for the introduction. If you're not familiar, my name is Torsney-Weir. I'm a lecturer in the computer science department. And this is sort of joint work with Alma Rahat and Dan Archambault, who are also in the computer science department, and a lot of student work from Rodri Fadbro, Finlay Gibson, who are both students working on this project. And then there's been a lot of guidance from Biagio, from the math department, and Michael Gravener from the medical school on putting all of this together. So it's a big joint project, and it has a very long title, which doesn't fit on one line on the slide, called Enhancing Hospital Capacity Predictions with Epidemiological Models. And that's very fancy and technical. To sort of start with the solution, basically what we're trying to do is predict hospital beds, like how many hospital beds a particular hospital will need in the next kind of 2 to 3 weeks. And the main problem they were having now, they have an existing way of doing this, but now there's an epidemic, if you've heard. And that's kind of changing how they want to do hospital beds. And so we kind of integrated as part of this Sarah Cumry grant, kind of integrating an epidemiological model with a fitting procedure, and then an interactive visualization tool to allow people to kind of understand how the epidemic might affect how many hospital beds the hospital actually needs to prepare. And yeah, so and this we've also been working together with the TAG. I think it's called the TAG group for Wales, and they basically kind of, it's like this sort of like a scientific recommendation board for the Welsh government that we've been showing this to, and yeah, we're working on trying to integrate this into actual hospitals. So the problem is this is what hospitals, people come in, they're sick, they need beds. I actually talked to my sister the other day and asked her, like, where are hospital beds? And she's like, oh yeah, they're in the closet. They're in a closet in a hospital, and it takes a little bit to prepare them, and you need to kind of have a good sense for when are they, like, you know, how many people are going to come into the hospital in the next few days. So hospitals need to know how many beds they need to prepare, because, you know, and they don't, you know, obviously you don't know when people will get sick or injured. So they basically need to predict this. The way it currently works at the hospitals is there's a statistician at every single hospital, and part of their job is to look at take the last 14 days of admissions to that particular hospital. And they fit two different statistical models. So one is they basically fit a linear regression on the admissions. And then one, they fit an exponential model on the admissions. And then they look at the kind of these two results over the next 14 days, and then try to, based on that, they basically, they make a recommendation for how many hospital beds the hospital needs to prepare for the next 2 weeks. And then, you know, that goes to the people who actually prepare the beds and all that. And that's how the whole process works. So they're basically using relatively simple models of how many people are going to come into the hospital. It's kind of okay because they're only predicting 14 days out. So nothing super complicated will happen until COVID happened. And so now what they want is they want kind of a better estimate for how will the current kind of status of the epidemic affect hospital bed utilization. So what they want to use now is like a special kind of compartmental epidemiological model called an SEIR model. I'll explain that in a second. But they also want kind of a way to sort of understand, you know, there's this whole idea of this infection rate that shows up a lot in the news, but, like, you know, it's like 1.2 or 1.1 or 0.9. And they want to understand, like, okay, well, if the infection rate changes, how will that affect how many people will come into the hospital? And then a general goal is also, like, these people are busy. They are not experts in epidemiological studies or models or or complex partial differential equations. And so the idea with the whole interface and the fitting process is to try and make everything as like simple as possible, and only kind of maintain, kind of keep the kind of key parts of the interface. And so this is actually kind of a challenge, right? So it's in some sense you can add a lot of bells and whistles to any sort of program or interface or something, but like pulling stuff away and figuring out just exactly what do you need to make it useful is quite complicated. So if you're not familiar with epidemiological, like these compartmental models for epidemiology, this is an example of one. This is the SEIR model that we were using in in this project. There's kind of four, basically what happens is everyone gets divided up. There's basically four buckets. So susceptible, exposed, infectious, and recovered. Susceptible is basically means you have not, if you think about it in terms of COVID, susceptible means you have not yet had COVID. So therefore you are susceptible to getting the disease. Also, you haven't been, now there's vaccinations, so you haven't been vaccinated. So essentially means you can get COVID. So typically when these models start is most people are susceptible because most of the population is not infected. Then what happens is somebody who has COVID transmits the disease to you, and then you become what is called exposed, which means you now have COVID in your body, and your body is now fighting COVID. However, it hasn't, like, I actually don't know the medical reason for this, but essentially you can't give other people COVID at this point. There's sort of an incubation period. But after that incubation period is over, I think with COVID, it's like 2 weeks or something. Then you become infectious. What did Dan just, oh, it is 2 weeks. Great.
No, it's 4 days. Sorry.
Oh, it's 4 days. Okay, so it's much shorter. So anyway, so from exposed to infectious, I guess is 4 days. So after 4 days, then you can transmit COVID to other people. And so you'll move from this exposed bucket to infectious. And then after a period of time, so the bucket is called recovered. So you get over the disease, or you unfortunately pass away or something. But regardless, you no longer have the disease at the recovered stage. And so basically the way these models work is you can vary the rates at which people move from susceptible to exposed, and from exposed to infectious, and from infectious to recovered. And based on how these rates work and the kind of relative sizes, or the relative numbers of people in each one of these buckets, that affects how the disease is progressing. Yeah, and there's a bunch of different parameters for this SEIR model. They have very intuitive names, so alpha, beta, and gamma. And so alpha is related to it's the time that from being exposed to becoming infectious. So this is actually basically disease dependent, right? So as Dan said, COVID is 4 days. So he basically set alpha to 0.25. Beta is essentially the probability that you would get exposed to COVID. So this is kind of a combination of like how many people you interact with, plus like how transmittable the disease is. And then gamma is the recovery rate. So this is essentially how long it takes to go from infectious to recovered. And the infection rate that gets quoted all over the news and things, this is just beta divided by gamma. For this particular model. So this is the model we had, and what basically the fitting process is trying to figure out with some initial parameters based on like Welsh population and things, how many, what are the current sizes of susceptible, exposed, infectious, recovered, and what is a good value for the probability of being exposed. Alpha and gamma luckily are actually fixed because we know they kind of know them because they know how COVID works at this point. So that those are fixed. So you basically need to fit 5 parameters based on this historical 14 points of data. That's what we do. So we take this SEIR model, we take the last 14 days of hospital admissions, we basically run a fitting process to find the kind of least error fit to this 14 days of hospital admissions. And then we put all of that together into an interface that we show to the user on the screen. And I have a demo, which I think, uh-oh, what screen did I put it on? I put it on the screen. So basically this is the interface that people see. Up here you have this model parameters area. So this basically shows you the values from the fit. And if you think these values are not good or don't make any sense or something, you can change them and it will change the predictions of the model. So I'll show that in a second. And then down here is actually the chart, which shows how the model, the various fits of the data points. So here you have on the y-axis, you have how many beds are basically going to be needed. And on the x-axis, you have the current date. So today's date is actually this dashed line, kind of in the middle left of the figure. So everything before that date, that's basically historical, and everything after that date is a prediction. These blue dots, these are the actual numbers of beds that were needed on those particular days, right? So those are the data points that we're basically fitting to. And then we fit basically two different models. So one is just this linear model, which they were fitting before. So that's this blue line. So this blue line is basically showing what a linear projection of the number of hospital beds needed would be. And then this dark green line, this is the fit of the SEIR model. And you can see that it has this much more complex shape to it because it's a much more complicated model. Yeah, and from that you can actually try and get a sense for like how good is it, how good is the fit to the data points and all this kind of stuff. So you can kind of get a visual intuition of this. The main interaction point is actually this R slider. And what this does is it basically changes the infection rate for the disease. But if you kind of, I don't know, if you go on the news and you're like, okay, well, I think, the current infection rate is this, but I know, they're, I don't know, reopening like a lot of large gatherings. And like, so what happens if the infection rate happens to go up quite a bit? You can kind of play with this slider, and this light green line changes in real time to kind of show you how the projection of the number of hospital beds that you need will change with the changes in the infection rate. So it's nice, and you get also, as you move this slider, you can get a sense for like how quickly are how is it going to go from like needing 10 hospital beds to 100, or is it going to go from needing 10 hospital beds to 11, which is quite a little bit easier to handle. So that's the kind of main interaction with this thing. The other thing people can do, is they really want, is they can override the initial fitting parameters. So you can say, I don't know, I don't think that many people are I think a lot more people are infected. So you can change it from, and you will get a change in real time. So the SEIR model is actually embedded in the interface, so we can just query it easily. We can run the model very easily in essentially interactive time, and so the user can make changes and very quickly see how those changes affect the result. So that's the whole idea with this interface. And yeah, this is just a big picture of it in case the demo didn't work, but the demo worked, so it's great. In terms of future work, is to kind of build. So right now it's estimating the number of people coming to the hospital based on how many people are currently infectious. What we especially like Alma and his kind of team with Finley is working on is kind of incorporating a much more robust model that specifically tries to predict how many people will show up to the hospital in a special type of compartmental model. And we're going to integrate that eventually into a future version of this tool. And then also, we just received an EPSRC grant, which is exciting, with Alma as the PI, and working on trying to understand how like different types of interventions can try and predict how different interventions can affect like say rates of hospitalizations or deaths or all this kind of stuff. And so this is kind of combining, similar to this tool, which was combining modeling with a visualization tool. This is also going to be a visualization tool combined with modeling. And so that's future work. And with that, thank you very much for listening. And I'm happy to answer any questions you have.